Right now, sitting in a sealed plastic tank in this yard, there's a batch of table scraps and manure that nobody wants to touch, and it's making fire, not metaphorically, an actual blue flame, burning off a gas that came from garbage with no propane truck, no gas line, and no bill. The whole system is a sealed tank, a gas line, and a bag that inflates as the tank works. Total cost is nowhere near what a propane hookup costs to install, and the fuel is stuff you were already throwing away. Here's the part that should bother you. This tank has no heater, no stirrer, no pump, nothing running it. It just sits there, sealed, and gas keeps coming out. That looks like it shouldn't work. I'll show you exactly what's happening inside, and why sealing out the one thing every fire needs is precisely what makes this fire possible. By the end of this video, you'll understand how anaerobic bacteria turn waste into fuel, how to build and vent this system safely, and the two safety limits that are absolutely not optional with this gas. Most people picture one of two things and both miss what matters. The first is a magic bucket. Toss in scraps, gas comes out immediately, free energy forever. That's not how bacteria work. They need weeks, not hours, and the air kept out completely. One bad seal and the whole batch stalls. The second picture is the opposite mistake, treating this as harmless because the inputs are just manure and food scraps. It isn't. The gas is a genuine fuel gas, flammable, carrying a toxic component that has killed people in enclosed sewage and digester spaces. Treating a homemade gas system like a compost bin, with no attention to sealing or venting, is what turns a science project into an emergency. The honest starting point is this. It's a slow biological process producing a real fuel gas, and it deserves the same respect you'd give a propane tank. Walk it through once, start to finish. Feedstock, manure, food scraps, plant waste, goes into the digester, a sealed tank with no air inside. Anaerobic bacteria, meaning bacteria that only work without oxygen, break that material down in stages over time, and the byproduct of that breakdown is biogas, mostly methane, mixed with carbon dioxide and a smaller amount of hydrogen sulfide. The gas doesn't stay in the digester. A gas line carries it out through fittings sealed for gas, not water, to a storage side, some kind of expandable holder that lets gas volume grow without pressure, building dangerously. From storage, the line runs to wherever it's used, a burner, or a generator set up to run on gas instead of gasoline or diesel. Leftover material that comes out the far end of the digester, called digestate, isn't gas. It's spent slurry, and it has to be handled and disposed of like any other effluent, not dumped into a sewer or storm drain. One sentence: bacteria eat what you can't burn and hand you back a gas you can. The core fact this whole system depends on: these bacteria are anaerobic, which means oxygen doesn't help them. It kills them. Seal the air out, and they get to work. Let air in, and they stop. Think of it like a campfire in reverse. A normal fire needs oxygen to burn fuel down into heat and gas. This tank does the opposite. It locks oxygen out entirely. A completely different set of organisms takes over the job of breaking fuel down. Except instead of releasing that energy as heat on the spot, they package it into a gas you can carry somewhere else and burn later on your terms. That's why every leak, gap, or loose fitting in this system is a double problem. It's not just gas getting out, it's oxygen getting in. And oxygen getting in is what stalls or kills the very bacteria producing your fuel. A sealed system isn't a nice-to-have here. It's the entire mechanism. The breakdown itself happens in stages. One group of bacteria breaks big molecules into smaller pieces. A second group turns those pieces into simple acids, and a final group consumes those acids and produces methane. Different bacteria, different jobs, one assembly line, running in the dark without air. Like any living process, colder conditions slow it down, and warmer conditions speed it up. Insulation or gentle warming helps consistency in a cold climate. The digester vessel. Practical DIY choices are 55-gallon plastic or steel drums for small setups, or IBC totes for a bigger step up. Both come with bungs that plumbing and gas fittings can thread into. The spec that matters is airtightness. Every seam and fitting has to hold a seal because this gas is corrosive on top of flammable. Why corrosive? Biogas carries hydrogen sulfide, and when that meets any moisture in the system, it forms sulfurous acid. That acid attacks cast iron and carbon steel through corrosion and embrittlement, and it attacks brass fittings too. Buy stainless steel, grade 304 or 316, for any metal fitting that touches the gas. For plastics, check temperature and chemical resistance. Polypropylene holds to roughly 185 degrees Fahrenheit, polyethylene to about 200. Regular PVC tops out around 140. For seals and O-rings, look for EPDM, Viton, or nitrile, chosen for resisting hydrocarbon gas and moisture. not whatever washer was in the drawer. The gas storage. I don't have verified capacities or prices for gas bags or floating drum holders for this scale of build. Compare current listings, but it has to expand as gas volume grows without letting pressure spike. The gas handling hardware. Standard water pressure gauges are far too coarse for this job. Biogas runs at very low pressure, so a simple water or liquid manometer is the practical way to read it. For valves in the gas line, again, stainless steel wetted parts and seals rated for gas. Nitrile for straightforward runs, Viton or PTFE where the gas is dirtier. I don't have verified numbers for how big a digester needs to be for a given amount of feedstock, or exactly how much gas a pound of manure or food scraps yields. I'm not going to hand you a made-up sizing formula. Size conservatively, start small, and expect to tune your system by observation rather than a spreadsheet. Biogas from digester systems runs at roughly 65 to 70% methane, with a heating value between 550 and 700 BTUs per cubic foot. Compare that to your propane tank. Propane carries about 90,000 BTUs per gallon at $2.25 to $3.25 a gallon. Natural gas itself runs 800 to 1,000 BTUs per cubic foot, so your biogas is doing real work just at roughly 2/3 the punch of the pipeline gas most stoves expect. One more number matters before this gas goes near an engine or stove: sulfur tolerance. Engines have historically been rated for only 10 to 30 grams of sulfur per 100 cubic feet before sulfurous acid starts eating valves and cylinder walls. Your specific manufacturer sets the real number, often tighter. Check the datasheet, and past that line, add a filter stage, pulling sulfur and moisture out before combustion. Phase 0. Paperwork before parts. Talk to your local building or code authority before you buy a single fitting. It's not exempt because you built it yourself. Phase 1. The vessel. Clean and pressure test your drum or tote before anything organic goes in it. Every bung and fitting checked for a seal that holds gas, not just liquid. Phase 2. Feed and seal. Load your feedstock, seal the tank completely, and resist the urge to open it and check on it. Every time you break that seal, you let oxygen back in and set the bacteria back. Phase 3. Gas line and storage. Run the gas line and materials rated for fuel gas, with stainless fittings, sloped and supported so condensation doesn't pool and block flow. Phase 4. The safety layer. Keep every spark-capable device at least 3 feet from the gas meter or regulator. Any electrical component near the tank or gas line needs to be outside the danger zone entirely, or rated explosion-proof. Mark any point where someone could physically enter the tank as a confined space. That label exists because people have died in exactly these spaces, and it is not decoration. Phase 5. Commissioning. Leak test every joint before you introduce any ignition source nearby. Soap solution, watched for bubbles, is the low-tech, effective method. Only bring a flame near the gas outlet once you've confirmed there isn't one anywhere else. Phase 6. Put it to use. Whether that's a burner or a converted generator, that connection needs matched fuel handling equipment, a regulator and gas-rated carburation set up for this specific gas, not gasoline hardware pressed into service. Failure 1. The silent stall. Symptom: gas production slows or stops, and nothing looks wrong from the outside. 'Cause oxygen got into the tank, a loose fitting, a seal that failed, a lid opened out of curiosity. Fix, find, and reseal the leak, then give the batch time to recover. Failure 2. The corroded fitting. Symptom: a brass or steel valve seizes, weeps, or fails outright after a few months in service. Cause: hydrogen sulfide meeting moisture, forming sulfurous acid, which eats ordinary metals from the inside. Fix: replace with stainless steel and gas-rated seals from the start. Pay once, correctly. Failure 3. The confined space mistake. Symptom: someone plans to physically enter the tank to clean or inspect it, 'cause not treating the tank interior as a space that can hold flammable gas, displaced oxygen, and toxic hydrogen sulfide all at once invisibly. Fix: never enter without following formal confined space procedure. That means a professional. This is the one failure mode on this list that can kill you, not just cost you money. Here's what's actually required. Wherever you are, gas-producing equipment and gas piping need a permit and inspection. This falls under fuel gas code, not plumbing code. Small does not mean unregulated. Find out which local fuel gas and environmental standards apply to you before you build, not after. The gas line rule that is absolute. Keep spark-capable equipment and ignition sources at least 3 feet from your gas meter or regulator. Digestate cannot be dumped into a sewer, storm drain, or waterway. It has to be handled as effluent, through an approved disposal path. And here's what I won't do. Hand you a specific safe exposure number for hydrogen sulfide or a flammability percentage for methane. Get the current OSHA or NIOSH thresholds and confined space procedure from a professional. Guessing at a number for a gas that can be lethal in a confined space is not a corner anyone should cut, including me. This video is educational and not professional electrical, plumbing, or structural advice. Have your plan checked by a licensed professional and your local code office before you build. I'm not going to hand you a total build cost, drum or tote, gas storage, valves, and any generator conversion kit. All move in price, and I don't have verified figures for a small-scale build. What's verified is the trade you're making. Waste converted into a gas running at 550 to 700 BTUs per cubic foot. Real fuel. Sitting somewhere between propane and pipeline natural gas in energy density. This isn't a project you rush. It's the slowest build on this channel. And if you're building a self-reliant homestead the right way, understanding the biology instead of copying a diagram, this is one of the deepest systems you'll put in your yard. On screen one more time. Educational only. Verify against your local code. Build it once, understand it forever. Subscribe if you want the rest of your homestead explained the same way.